Hello everyone. In this video, we are happy to introduce our work, MoDAR using motion forecasting for 3D object detection in point cloud sequences. Effectively leveraging sequence data in 3D detection can potentially help difficult cases such as occluded or long-range detection. However, naively adding more frames to existing methods such as center point and SW former quickly plateaus improvements, while our method, MoDAR, scales up to many more frames and gets much larger gains. In this work, we propose using motion forecasting outputs as a type of virtual modality to augment LiDAR point clouds. The MoDAR modality propagates object information from temporal context to a target frame, represented as a set of virtual points, which are colored here in red and blue. A fused point cloud of both raw sensor points and the virtual points can then be fed to any off-the-shelf point cloud-based 3D object detector. We will start with related works and then move on to the method, experimental results, conclusion, and some future directions. In this work, we are focusing on 3D object detection on point clouds. Specifically, given point clouds captured by LiDAR, our goal is to detect 3D objects. To improve the detection accuracy, previous works have found that taking multiple LiDAR frames as input is very helpful. Point concatenation is a simple way to achieve this goal, which directly concatenates the multi-frame point clouds together into the target frame coordinates. This method is mainly effective for stationary objects, but is less effective for moving objects as shown in the bottom figure. When applying point concatenation to SW former, which is a prior state-of-the-art 3D detector that uses transformers, we observed that while detection accuracy improves when using more input frames, we quickly run out of memory. This out of memory is caused by concatenating too many points. When applying point concatenation to center point, a widely used architecture for detection, we observe that the detection accuracy quickly plateaus as we add more input frames. We speculate that the performance saturation is due to misalignment of moving objects. While there are challenges to improve 3D detectors simply by stacking frames, recently there is a new trend in developing off-board detectors that access both future frames and past frames and have vastly different formulations as onboard ones. Such methods have shown strong improvements on popular single-frame detectors designed for onboard use cases. In the off-board setting, an idea came to us that we can leverage the motion forecasting models to help 3D detection with sequence data. In motion forecasting, the goal is to predict the future trajectories of different road users. Such models are becoming more and more mature and powerful in the recent years. Such prediction can help align moving objects into a joint coordinate system, such that information from distance can be connected to help improve 3D detection. This idea leads to our proposed method. Using motion forecasting, we generate virtual points that we call MoDAR points, marked in red and blue. Motion forecasting based detection and ranging, which is named after a similar fashion to LiDAR. Note that for an off-board system, we can have reverse motion forecasting to predict the past trajectories from future observations. Any point cloud-based detectors can then take the union of MoDAR and LiDAR points for 3D detection. In the next slide, we will introduce in more detail about how to generate MoDAR points from a sequence of LiDAR point clouds. Given a sequence of point clouds, we first apply sliding windows to get as many as 11 frame subsequences as input to a motion forecasting model. Then we run motion forecasting on these subsequences. Motion forecasting works by running a pre-trained detector, tracker, and trajectory prediction model sequentially. The MoDAR points include channels such as the coordinates of predicted object center locations and point features of additional object status information such as 3D bounding box size, object type, detection score, and so forth. Finally, we union the LiDAR and MoDAR points and train a LiDAR-MoDAR 3D detector to get our final detection results. Next, we will show some experimental results. Evaluated on the Waymo open dataset, adding MoDAR to LiDAR points significantly improves all base detectors. For example, MoDAR improves LiDAR augment by 5.6 mean APH from 72.9 to 78.5. This is a new state-of-the-art result without model ensembling. For ablation studies, this table shows the effect of different object state features. It turns out that the object location is the most important information stored in the MoDAR points. We also observed that MoDAR especially helps with detecting long-range objects. As shown in the table, MoDAR improves performance by 12.9 APH for vehicles beyond 50 meters. In this figure, we see that long-term information is also helpful. The red bars on the left are the performance of models using only MoDAR points generated from the past frames, while the green bars on the right are results of models that use the same number of past and future frames for MoDAR point generation. We can see that using both more MoDAR points from more frames, as well as using both forward and reverse motion forecasting, helps improve detection accuracy. To conclude, we propose MoDAR, a virtual modality for motion forecasting model that leverages both previous and future temporal information. We can fuse MoDAR and LiDAR to achieve more robust detection results, especially for occluded and long-range cases. The method is generic and applicable to any point cloud-based 3D detector. Specifically, based MoDAR on top of the LiDAR augment detector, we achieved state-of-the-art results on the Waymo Open dataset. As for future work, besides offboard detection, we can design offboard motion forecasting models to further improve accuracies of the MoDAR points. For onboard purposes, we will study the interdependence between the detection and the motion forecasting models towards end-to-end detection and prediction. Thank you for your attention, and we're looking forward to seeing you during our poster session.